Video, we're going to look at how we can evaluate the trig ratios of any given angle, not just acute angles in a given right triangle. So what we're going to do is we're going to start by extending our SOHCAHTOA definition of the, trig functions of an angle that is an acute angle in a right triangle, and extend it out to be more generally speaking, look, any given angle, could we find the sine, cosine, or tangent, not just these acute angles. So we're going to kind of reimagine our angles here. Just slightly. So we still are going to consider our angle as an angle in standard position here. So maybe I have some angle that terminates in the first quadrant, and here's my theta. But in terms of how we're going to reimagine this here, I want us to imagine that there is a circle of radius r that is also centered at the origin, or the vertex of our angle here. And we can see that this radius here would be our r. As a matter of fact, I'll go back and put that in a moment. What we want to kind of probably focus on first is just that our terminal ray of our angle has to intersect this circle of radius r somewhere at some point, and we're going to refer to this point as x comma y. The interesting thing here is that kind of imagining it this way, is this terminal ray intersecting the circle of radius r, is we can always take from this point and drop an altitude back to the x-axis here. And what you're going to see is that we form this right angle right there. And so we get this triangular space here. And in terms of, do we know any parts of this triangle? I suppose we know that because we know this point xy on the terminal side where it intersected the circle, we would know this distance and this distance right here. As a matter of fact, the only distance that we would know on this triangle would be this distance from the vertex of our angle out to this point where our terminal side intersects the circle. And this distance back from this point to the origin is always going to be referred to as r, and specifically because that's the radius of our circle right here. But kind of imagining things this way, any angle in standard position can be thought to intersect a circle of radius r at this point xy. Well, then we can kind of imagine things this way and redefine our sine, cosine, and tangent just using our SOHCAHTOA trig. So, SOHCAHTOA, if I can write this here, tan of theta. We know that our sine of our angle is opposite over hypotenuse, cosine is adjacent over hypotenuse, and then we have opposite over adjacent for our tangent. We can kind of imagine this then being, looking at this angle theta, opposite over hypotenuse, which would be y over r is our sine. Cosine would be x over r, adjacent side over hypotenuse, and then last but not least we would get opposite over adjacent, which kind of gives us a y over x configuration here. So we're going to use this definition of our trig functions, and likewise we can define the 6 trig ratios that are the reciprocals of these just by flipping them over, but we're going to define them this way. So with respect to what we're going to be looking at, is we're going to be looking at angles in standard position where we're given a point on the terminal side. Okay. In this particular case, you can see that we're given the point 4, -3 on the terminal side of this angle. So things to recognize: our angle's in standard position, our terminal ray passes through this point xy, and it looks like we have a clockwise or a negative angle rotation here. What I want to do is, I want to, from this point, kind of drop an altitude right here back to the x-axis, and what we're going to do is imagine this as kind of being a triangle. What points, or sorry, what sides would we know? We would know that the x value here is 4. We also know that the y value here is a -3, and we are going to put a -3 there. The only thing that we tend to be missing at the moment is just this value of our distance from this point back to the origin, r. So how are we going to find r? Well, the neat thing about this is just, this is a Pythagorean relationship. So always is true, x squared plus y squared equals r squared, and it kind of follows that r would therefore be kind of the square root of x squared plus y squared if we take the square root of both sides of this. But I want to make sure we write this down. It just means that if you know your x and your y, which is always this point on the terminal side, then you can find r, and one quick note we want to write is r is always positive. X and y may be negative, but man, r is always positive. So looking at something like this here, one of the first things we'll want to do is find the value of r. We say x squared plus y is a -3 squared is r squared. We would get 16 plus 9 is r squared. It would follow that 25 equals r squared, and that we get plus or minus 5 is our root of 25, but we're going to keep the positive one just because r is always positive. So in order to be successful at these, the one piece of advice I'm always going to give is just off on the side, find a spot, and we're going to write in these data values here, x, y, and r, because in order to find these ratios, we need those 3 values. So our x value is 4, our y value is 3, and those were given to us, but our r value we determined was 5. So now we can use either the picture or these letters to help us inform us about these ratios, but I think both are meaningful here. So for our sine ratio, I know sine is y over r. Look, my y value, guys, is -3. Our r value is 5, excuse me. When you look at this triangle, this being our inner angle here, opposite over hypotenuse, you certainly do get negative 3 over 5. So I can use the triangle to inform myself as well. Our cosine is x over r. Well, that's going to give me 4 over 5 here. It's my x over my r, or adjacent over hypotenuse. Okay, and then our tangent would be y over x, in this case negative 3 over 5. So to get our other three ratios down here, again, we're just going to flip the initial 3 over. There are some things that would be worth mentioning here. So one of the first things I want to mention is just this. You'll notice that out of all of these trig ratios, cosine was positive. Cosine was positive, and secant, its reciprocal, was also positive. Everything else was negative. So this just goes to show that because we're defining these as x over r and y over x, since r is always positive, our sine values or our cosine values being positive or negative kind of depend on whether you had a positive or a negative x or y value. So because we're in the fourth quadrant here and we have a negative y value, we tend to see things like our sine values be negative. Or tangent, which is this ratio of y to x, a negative over a positive would also be negative here. So we tend to realize that some of our trig functions will be negative depending upon the quadrant we terminate in. And the other thing is just that if, say, cosine is positive here, its reciprocal also is positive. If anything is negative, then its reciprocal is also negative. So I wanted to try this again here using this definition. This time, though, we're going to illustrate our own angle and standard position. So looking at this number 5 here, what we know is that there's a point 2, negative 3 on the terminal side. My position is that you should always graph the point first. And so I know that going right and going down is going to place us in the fourth quadrant. And I notice that I'm going further down than I'm going right. So when I illustrate this, it doesn't have to have notch marks on here. As a matter of fact, I'm kind of opposed to having notch marks. I would just say that I went further down than I went right, and I'm just going to call this the point 2, negative 3. So what do I know? Well, my angle in standard position starts on the positive x-axis, and my terminal ray passes through this point. So my angle in standard position, it's up to us whether we want to put it here, do a clockwise rotation, or if we want to go all the way around. Thing is, it's not going to matter. So I'm going to make mine a counterclockwise or positive angle rotation, and I'm going to drop my altitude back to the x-axis. And in a similar fashion, we're going to fill out what we know and find what we don't know. So we know our x value is 2, our y value is negative 3, and this third side is r. Let's pick it up a little bit on this one here. We say that r is always the square root of 2 squared plus negative 3 squared. This is just our Pythagoras here. So we get the square root of 4 plus 9, or in other words, the square root of 13. And this is kind of how I want you to leave it, the square root of 13. So putting our little index off on the side here, x equals y equals r equals, we get x equals 2, y equals negative 3, and r in this case is just positive root 13. So using these, let's go ahead and put our ratios together. Sine is y over r, so negative 3 over the square root of 13. Cosine is x over r, so 2 over root 13. And then our tangent's y over x, or negative 3 over 2. And before I start rationalizing denominators here, I'm going to flip all these over, so I would also get negative root 13 over 3 is my cosecant. Positive root 13 over 2 is my secant, and then we'd get negative 2/3 is our tangent. So like we mentioned, we do need to rationalize the denominators here and here, but we would get negative 3 root 13 over 13 as our final value, and here we would get 2 root 13 over 13 as our final value. So what I want to see going forward is that you can sketch your angles in standard position, and using this point on the terminal side, kind of find two sides of the triangle that you've kind of constructed here. And then we can find the hypotenuse just using Pythagoras. But beyond that, we're going to define our sine, cosine, and tangent of any angle, just given these three ratios right here, y over r, x over r, and y over x. Cheers.